Jai Hind everyone. I am Dr. Suman Godwal, working as an assistant professor in the Department of Mechanical Engineering at AKGEC Engineering College, Ghaziabad. So in today's lecture, we are continuing the same subject, that is operation research, and the target students will be the BTech 4th year students and MTech 1st year students. And here I have written the MTech code, that is MTME 102. Now, in today's lecture, we are going to discuss about the classification of the LPP solutions. Means when we solve the LPP problems, we get different types of solutions. And in today's lecture, we are going to discuss these in details. And after that, we will take some example which are based on the graphical methods. So, classification of LPP solutions and problem based on graphical methods. Now, first we will discuss about the outline of today's lecture. So, first we will classify the LPP solutions, and after that, during the classification, we will see different type of solutions that we can obtain. So, first one is the feasible solution, then the infeasible solution, unbound solution, and the multi-point solution. Okay, then we will take some example which are based on these type of solutions. So first we will see, or we will talk about the feasible solution. So what is the meaning of the feasible solution? A feasible solution is the set of possible values for decision variables that meets all the constraints and does not violate any of the constraints. Okay, so we will get the decision variables value here, and these decision variable values will meet all the constraints. These will not violate any constraints. For example, if we see in this graph, so we can see here there are two constraints involved, constraint 1 and constraint 2. And we have discussed in our previous class that for plotting the constraints on the graph, first we convert these constraints into the equations and we plot these equations onto the graph. So we had the two constraints here and we converted it into the equations and then plotted it on the graph. Now after that we will find out the feasible region, or we will shade the common region. So and it will depend, the shading area will basically depend on what type of symbol is associated with the constraints. If it is greater than equal to symbol, then what we are going to do, we will shade above the line, and if this symbol is involved in the constraints, then we are going to shade below the line. So we can see here that here we are shading below the line. It means this symbol is associated with this. After that, we will find out the common feasible region. So we can see here, this is the common feasible region in constraint 1 and constraint 2. This is the feasible area. Okay, and we can see here these are the corner points. These are the basically 4 corner points. So we know the coordinate of this point, means x2 coordinates we already know. We know the coordinates at this point also. Okay, and this is the intersecting point. We want to find out the coordinate of this intersecting point. So these are the points which are touching or lying on the common feasible region. Okay, so here we will get the value of their decision variables which are not violating any of the constraint. Okay, so this is basically the feasible region, and we will get the solution from these 3 points. So this is the feasible solution. We will get the feasible solution here. After that, we come to the second type of solution, that is infeasible solution. So infeasible solution is basically, it will violate at least one of the constraint. Okay, it will not follow one of the constraint, at least one of the constraints, and one of the constraints does not touch the feasible region. in the previous section or in the previous type of solution, that was the feasible solution, we saw that both the constraints or both the points are touching, both the all the points or the corner points are touching both the constraints. Okay, but here in case of the infeasible solution, it is saying that one of the constraint does not touch the feasible region. Okay, it will not touch the feasible region, then the solution is infeasible. So in that case, we will say that our solution is infeasible. There is no optimal solution and we will not get any solution because the constraint is not touching the feasible region. So we will not get any optimal solution. For example, we have taken this example. This is the objective function where we have taken the example as max z is equal to 2x1 plus 6x2. Okay, we want to maximize the objective here, and this is subjected to these two constraints. These are the constraints here, and this is the non-negativity restrictions are defined here. x1, x2 greater than equal to 0. Now what we do, we will first convert these constraints into the equations with the help of the equality sign, and after that we will plot these lines. We have plotted these lines. Okay, this is the x1, this one is x2. Okay, this coordinate is 3, 4, 4 and 8. These are the coordinates. These are both the lines are plotted on the graph. Now we will shade the region. Okay, so we can see here this less than equal to symbol is involved, means in this case. Okay, so here we will shade below the line. Clear? But in this constraint there is greater than equal to symbol, so we will shade above the line. Okay, now we find out the common region. Okay, common feasible region, but we can see here that the constraints are not touching each other. In one of the constraint we have shaded below the line and the other constraint we have shaded above the line, means there is no feasible or there is no common feasible region. So here we will not get any solution. Clear? So this is the example of the infeasible solution. Now we come to the unbound solution. So unbound means which is not bounded, which has no limits. Okay, so it exists when LP problem has no limits on the constraints, means there is no limit on the constraints. It is not bounded. The feasible region is not bounded in any respects, means we will have the feasible region but there is no boundary. Okay, there is no limitation. There is feasible region but the boundary of that region is not defined. For example, we have taken this objective function max z is equal to 3x1 4x2, which is subjected to x1 plus x2 greater than equal to 5 and 3x1 plus x2 greater than equal to 8, and these are the non-negativity restrictions are defined here. Now what we did, we have plotted both the equations onto the graph and after that we will shade the region. So here we can see in both the constraints greater than equal to symbol is involved, so we will shade above the line. So we have shaded above the line, but we can see here the common feasible region is this one, but it is not having any boundaries. So this type of solution are known as the unbound solution. Now we come to the multi-point solution. We will when we will get the more than one solution. Multi-point solution means we will get the same value of the objective function more than one point. Okay, so when in linear programming problem we have same optimal value of objective function, we will get the same value of the objective function at more than one corner point, then the solution is said to be the multi-point solution. For example, here we have taken the example as maximum z is equal to $40x1 plus $30 x2, which is subjected to x1 plus 2x2 less than equal to 40 and 4x1 plus 3x2 less than equal to 120, and these are the no negativity restrictions x1 and x2 greater than equal to 0. Here this x1 is the number of balls and these are the number of mugs. X2 is number of mugs. So we have already discussed this example in our previous lectures. So we have plotted these lines, both the lines we have plotted here, and okay, we can see here we get the three corner points, okay, this A, B and C. So we know the coordinate of this one, we know the coordinate of this one, and we can find out the coordinates of point P by solving these two equations. Okay, so we got this as the 24 and 8. Okay, after solving these two equations, we will get the coordinates of P as 24 and 8. Now what we will do, we will put the values of all these coordinates in the Z. Okay, so we can see here at point B and point C we are getting the same value. So this type of solution where we are getting the same value of the objective function at more than one point is known as the multi-point solution. Now we have taken one example here. Here we will see how we will formulate the LP problem, and after that we will solve it with the help of the graphical solution or graphical method. So the example is ABC Limited has two bottling plants. Okay, there are two bottling plants. One is located at L and the other is located at M. So there are two bottling plants and one location. The one plant location is at L and the other plant location is at M. Okay, each plant produces 3 brands of fruit juice. So the 3 types of juices are produced at each plant: fruity, orange and tropicana respectively. The number of bottles produced per day, demand of each brand for the month of June, and operating cost of each plant are as follows. So some data is given about the juices. Okay, the bottle of juices at the plant L and M. The demand is also given for the month June, and the operating cost per day for at the plant L and the plant M is also given. So we can see here the Tropicana juice. For Tropicana juice, the number of bottles that are produced are 1500. Okay, and for plant M it is 1500, and the demand for the month of June is 20,000. Okay, for orange it is 3000 at plant L and 1000 at plant M, and the demand is 40,000. For fruity it is 2000 at plant L and 5000 at plant M, and the demand is 44,000. Now the operating cost per day for the plant L is 600 rupees and for plant M it is 400 rupees. Now they are asking how many days plant will run in the month of June to satisfy the demand at optimal operating cost. Okay, so these they want the optimal operating cost, means how many days the plant should run, each plant should run, so that the optimum cost become optimal. Means we want to minimize our cost, so it is the problem of minimization. Okay, so this is the descriptive statement which is given to us. So first step will be to formulate this problem, means we will convert the descriptive statement into the mathematical format. Okay, now we will write the equation for this as, first we will define the decision variables. So when we will define the decision variables, we write down as, we have taken the decision variables as x1 and x2. Okay, So x1 is basically the number of days plant L operates in month of June. Okay, and this is the number of days plant M operates in the month of June. Okay, these are our decision variables. Now what we will do, we will write down the objective function. So objective function is minimize the operating cost. So minimum Z, we will see 600 x1 plus 400 x2. Okay, it will become 600 x1 plus 400 x2. Okay, this is our objective function. Now we will write down the constraints. So we will write here subjected to subjected to. Now we will see the details for plant L for the Tropicana. It is 1500 and the demand is 20,000. So we have to produce more than the demands. Okay, we cannot produce less than the demand. So it will become 1500 x1 plus 1500 x2 greater than equal to 20,000. Okay, so the first constraint will be 1500 x1 plus 1500 x2 greater than equal to 20,000. Okay, this is the first constraint. Now we will see the second. For orange, it is 3000 x1 plus 1000 x2 greater than equal to 40,000. So we'll write down 3000 x1 plus 1000 x2 greater than equal to 40,000. Now for the third constraint, we will write down 2000 x1 plus 5000 x2 greater than equal to 44,000. So we will write down 2000 x1 plus 5000 x2 greater than equal to 44,000. So these are our constraints. Okay, and now we will define the non-negativity restrictions x1 x2 greater than equal to 0. So this is basically our formulation of the problem. Okay, after that what we will do, we will plot these lines on the graph. Okay, so for example, if this one is our graph, okay, this one is x1, this is your x2. Okay, so first we will convert it constraint into the equations. It was 20,000. Okay, we will find out the value of x1 and x2. So if x1 is equal to 0, x2 comes out to be 40 by 3. If x2 is equal to 0, x1 comes out to be 40 by 3. So the x1 x2 is 13.33 comma 13.33. Okay, and the same manner we will find out the coordinates for the equation 2 and 3 also, and after that we will plot all the lines. This is for the first. Now we will find out for the second. 3000 x1 plus 1000 x2 is equal to 40,000. So when we will solve it, we will get x1 is equal to 0, x2 is equal to 40, and when x2 is equal to 0, we get x1 as 40 by 3. The coordinates क्या हुआ? हो जाएगा x1 x2 is 13.33, 40. Okay, this is for third. Now for the third, what will be the 2000 x1 plus 5000 x2, 44,000. Okay, this is the third constraint. So when we will solve it, x1 is 0, so x2 comes out to be 44.5, and when x2 is equal to 0, x1 comes out to be 22. So coordinates क्या हो जाएंगे? x1, x2 equal to 22 and 8.8. Okay, now the next step is to plot these coordinates or plot these lines on the graph. So when we will plot these 13.33, 13.33. Okay, this is 13.33 and this is also 13.33. Okay, this is our first line. Okay, for second we will plot. For second, it is the coordinates are 13.5. The coordinates are 13.33 and 40. Okay, so for example, this one is 40. Yes, this one is same. This is 40. Okay, so this is the second line. Now we will plot the third line. This is 22 and 8.8. So 22, if 22 is here, 8.8 is here. Okay, so this line will become like this. So this is the third line. Now we will shade the region and we will find out the common region, visible region. So we can see here the symbol which was involved is the greater than equal to symbol. Okay, it means we will shade above the line. Okay, so this will be the common region. Okay, in all the three cases we will shade above the line. So this is the common region. So we can say this is the unbound type condition. Okay, so if we see about the common points, so these will be the common points. Okay, this is the intersecting point, this one. Okay, this one is the intersecting point, and this intersecting point is coming by equation 3 and equation 2, second and third equation. So after solving the second and third equation, we can get this intersection point. Okay, so when we will solve this, we will get the coordinates as 12 and 4. Okay, we will get these coordinates. Now what we will do, we got these points 0, 40, this one, and 22, 0. These are 3 points which are common. Okay, now we will find out the value of Z at all these points. So what we will get, Z was 600 x1 plus 400 x2, and our coordinates are 0, 40, 12, 4 and 22 and 0. Okay, these are, so we will find out the value of Z at all these points. 600 into 0 plus 400 into 40 is equal to 16,000. Okay, and 600 into 12 plus 400 into 4 is equal to 8,800. 600 into 22 plus 400 into 0 is equal to 13,200. So these are the value of Z at the common points. So we can see here that we get the minimum value of Z at the coordinates 12 and 4, and this is 12 is the value of x1 and this 4 is the value of x2. Okay, and if we remember, the x1 was basically the number of days the plant L will operate in the month of June, and this was the number of days the plant M will operate in the month of June. So, and our objective was to optimize the operating cost. So here we are getting the minimum cost, means the coordinates which are against this are 12 and 4. It means the plant L will operate 12 days and the plant M will operate 4 days to optimize the operating cost. Okay. So in this way we can solve the other examples also. So this example is for the multi-point solutions, means we will get the optimum value of Z, same optimal value of Z at more than one point. So this is for your practice, you can practice it. This is the simple example and will be done in the same manner as we have discussed the previous example. This is all for today's lecture from my side. Thank you.